What's up, ladies and gentlemen? It's Mr. Simpkins in the Simpkins Physics Corner with a couple of pro tips for the AP Centripetal Force Lab. So in class, I demonstrated this little apparatus. Basically, you hold onto a straw. That's not me, by the way. You hold onto a straw and you swing this rubber stopper around in a horizontal circle above your head. Now, as you can imagine, if you swing that too slowly, this stopper is tied to a string which goes through the straw, comes down here, and is attached to this little hanging mass at the bottom. If that mass is too heavy, then you have to spin really fast, right? And if you spin too slow, the mass is going to come down. If you spin too fast, you can raise the mass up, kind of like an elevator, right? But if you spin it just right, all the forces are balanced. And this is the idea for the lab today. The reason that the stopper does a circle is because there is a centripetal force. So this idea of centripetal force, that means a force acting towards the center of a circle. What is the centripetal force? Well, the specific type of centripetal force is the string. Of tension. Here's the next question. Why is there tension in the string? Well, because the string is tied to this weight down here. And if this weight that's hanging at the bottom is not moving, if it's at rest, that means that the force of gravity on that weight, I'll call it FGH, force of gravity on the hanger, must be equal to the force of tension that's up. And then we throw Newton's third law for tension in there, the idea that the force of tension throughout a string is uniform throughout that string, and we get the following idea. The centripetal force is equal to the force of gravity on the hanger. Can you follow it? Can you follow it through? Look, the centripetal force is because of the force on the hanger. All right, so now the purpose of our lab is to determine the mass of this stopper without a balance. So we have to figure out what's the m, the little m of this thing. And we'll call this big M down here, the mass on the hanger. So the mass on the hanger we'll call big M. So over here, that's going to be m times g. And then, actually, you know what? I'm going to leave it as mass of the hanger. Let me just erase that real quick, because I'm going to show you how this works out here in a couple minutes. All right, cool. What we can say, though, is that the centripetal force is mv squared over r. All right, the mv squared over r, the m is the mass of the stopper, which is what we're looking for. The v squared is the tangential velocity, how fast the stopper is swinging around, and the radius is the radius of our apparatus here. So if I were to solve for m with a little algebra, it would look like this. It would be FGH times r, the r would come up, divided by v squared. See, the v squared would come down, the r would go up. Now, how might we get this value for m? Well, the radius we're going to keep constant. We're going to keep the radius consistent. And in the videos that I posted, my radius was 0.6 meters. So if you're using my videos from Canvas, those 5 trials, you're going to use 0.6 meters for your radius. But let's focus in on this right here. Here's something that we can do. Could I go measure the weight of one hanger mass and take one data point for velocity? Yeah, I could, but that would be garbage results, okay? Because in science we do multiple trials, and even better than multiple trials is determining the actual physical relationship between two variables. So here's a cool strategy that we're going to use a lot this year. If you can rearrange a physics equation and identify two things and set it up as a rise over run situation, then we can take the slope of a graph to determine the relationship between those two variables. What do you mean, Mr. Simpkins? Well, focus in on those brackets right there. The rise of my graph, if I make the rise of my graph, oops, sorry, that's a P, I don't know what that is. I make the rise of my graph FGH and the run of my graph V squared, right? Look, rise over run. Now I'm determining a relationship. So what we're going to do today is in the videos, I vary the mass, which varies the weight, right? And I give you guys 5 data points. And so instead of relying on one trial or one piece of data, or even, you couldn't take the average if you're varying the mass, right? So what we're going to do is we're going to vary the force of gravity on the hanger by varying the mass on the hanger, and we're going to measure the response of the velocity, but specifically the velocity squared, because of the way that our mass equation is set up over there. And this m, keep in mind, this is the slope, all right? M is the slope. Whatever this slope is going to tell us about the number in those brackets. Wow, that's pretty crazy. So at the end of this lab, after you look at the videos, time how long it takes to go around this a couple times, get the frequency and period, calculate the tangential velocity, square that tangential velocity and graph it versus the force of gravity on the hanger. Once you do all of that, once you make your graph for force of gravity on the hanger versus v squared, the slope is going to be here. So basically your final answer for the mass of the stopper is going to be the slope of your graph that you made times the radius. All right, and I posted the accepted mass for the rubber stopper to the Canvas page. Okay. Now, some of you have asked me, Mr. Simpkins, how do I do the calculated column on LoggerPro? You could just do the calculations for each velocity value individually, or you can make LoggerPro do the work for you. So let me switch to my running one that I have going here. And let me just demonstrate one more time how this would look from scratch. So let me get rid of this guy here. Oh, I don't want to get rid of the whole thing. So basically, the way I made this guy right here, let me delete this column. Let's say you plug in your values for velocity, and here's our values for force. Keep in mind, we want the force on the y-axis. So on the y-axis, we're going to put force, and on the x-axis, we have velocity. Right? So we notice that force and velocity have this quadratic or x squared relationship, and that makes sense if you look back at this equation. You see the f and the v squared, right? So those two things they're going to have some relationship with this squared idea. But what you're going to do is take your velocity, your calculated values for velocity, and you can make LoggerPro do a calculated column for you. The way you do that is you say data, new calculated column, and I'll call this velocity squared. The short name will be v squared. And my expression, this is like the formula you type in. You're going to say, hey, go to my velocity values. So I clicked on variables, columns, velocity, and then ℓ2 to square it. And when I click OK, you notice I got this blue column, v squared, right? So now it's calculated my square velocities. The final step to finish up your graph here, change the x-axis now to velocity squared. And when you do that, of course, you're going to drop your linear fit on there, and you're going to use whatever slope you got over here as your value that goes in the brackets of our derived equation right here for the mass. Okay, so there's a little strategy for the LoggerPro. You can make it do the calculations for v squared for you, or you can just start from the very beginning, square all your velocity values, and drop them in the LoggerPro. All right, so Godspeed with this one, and this will be a full lab report, so you can submit that to Canvas. This is Mr. Simpkins, the Simpkins Physics Corner, with Centripetal motion, Gangnam style. Take it easy. I can't stop this thing.